Hey everyone, this is Tyche's 10-second hotfire data review. Today we're going to be going over the hardware changes that we've done since the previous 3-second hotfire that we did, all of the changes going forward, and the data that we received during this 10-second hotfire.
10-second hotfire data review.
Today we're going to be going over the hardware changes that we've done since the previous 3-second hotfire that we did, all of the changes going forward, and the data that we received during this 10-second hotfire.
10-second hotfire data review.
Well as the current injector that we were using and what we learned from all of this. And lastly, we're going to talk about the data, the expected data versus the actual data that we received, all of the different pressures, tank, injector, chamber, the current injector that we were using, values, and what we learned from all of this. Temperatures, and lastly, we're going to talk about the data, the expected data versus the actual data that we received.
So some of the changes that we had after our 3-second hotfire that was at the beginning of May, I believe. First, we had our first use of a phenolic insert. We did not use that in our previous test for the 3-second. We kind of just tested it without the phenolic inserts as like a little base. But this time we used the phenolic insert to try to get to that 10-second goal of the hotfire. We also remanufactured our flange. The previous inner diameter of the flange was a bit too small, so we corrected that with the remachining. We also increased the flange lip size to increase the carbon wrap effectiveness.
All right, moving into the test day review. Here's the successes versus the shortcomings of the test day. Starting with the successes, we achieved a full duration burn, the 10 seconds that we were hoping for, which was amazing. Next, we provided a lot of substantial training for new test personnel. There was one brand new red team member, as well as two to three, one new TCON personnel and one new DAC personnel. So that was great training and good experience for all around. Next, we were pretty flexible with a couple of hurdles that happened during the test. We had a fuel pump failure at the beginning, so we had to switch to a manual fuel fill during the test. We also had some igniter trouble during setup, and which caused a couple of button resets, but we were able to work around that and eventually get to a 10-second burn. Next, the crowd management and the show up at the beginning was great. It was amazing to see the crowd that showed up and the crowd that stayed around even after a couple of button push resets. So that was really nice to see. Going into the shortcomings, we had multiple resets around the button push, one of them being due to a faulty igniter, the other one being due to faulty igniter installation. We lost a lot of pressure doing both those resets. So leading into the final one, we were definitely pushing our GN2 bottles for whatever pressure we could get and reaching that minimum that we were comfortable going to. As I mentioned, we had the fuel pump failure, which forced us to do a manual fuel fill, and which ultimately went better than expected and worked out in the end. And so that was a success out of a shortcoming. And lastly, there was a 5-voltage Pixie power fluctuations, which interrupted our ability to use MakeSense. And so we had to adapt around that on the fly. What did we learn? Actually, before we get into that, Mackenzie, would you like to share the perspective of the TCON during the test day?
Yeah, I'm Mackenzie Kelly. For those who don't know, I was the test controller or TCON for this day. The big thing about this day was a fantastic day. We had a huge success, a 10-second burn. Our biggest hurdles were, in fact, our igniter installation, blowing out the igniter on chill, which we'll talk about later. The fuel pump failure was just, could have planned ahead a little bit more. 5-volt power, yeah, inhibited some of our functionality during the test, but but it really wasn't that big of a deal. During the test day, overall, all of the shortcomings were met with some really great flexibility, and really well done for the test team.
Thank you. So what did we learn from this? One of the big things was definitely checking continuity of e-matches before installing the igniter to kind of prevent any of button or having to abort after button push. Definitely being careful of the installation to minimize these resets, allow us to keep the most amount of pressure in our system, as well as being a better kind of test day for the crowd as well, so that's not as long and drawn out. Next, we also, like Mackenzie said, checking the fuel pump multiple days in advance for making sure all of our equipment is working and prepared for. So that'll be a definitely big going forward, and that was something to definitely learn for the red team. And yeah. Next, we're going to move into the hardware review.
Starting off with we're going to talk about our phenolic insert. So first and foremost, this is the first hotfire in which we incorporated a linen phenolic insert in the throat. We believe that successfully extended the bird time to our 10-second mark that we're trying to hit. However, we couldn't have gone much longer. As our T-Con, or Mac over here can attest, he was about to abort the fire right when it finished because we were about to burn out. So that's awesome. Our phenolic and our chamber both experienced severe deformation, likely due to poor atomization from the injector. Which highlights the shortcomings of our ablative chamber. We have a very limited chamber life, especially on the diverging end of the engine, even with perfect mixing. During our fire, the ablation reached the carbon layer, so the very outside of the engine, and we had a lot of flaking in the inside silica. Although that flaking could be due to the quality of our personal silica wrapping. However, we did make some improvements from last fire. As mentioned previously, we changed the dimensions of our flange to better, to be less of a safety hazard. Due to the dimensions of our flange in the 3-second fire, our walls were very thin, coming out to about 75 thousandths of an inch. This fire, we increased that to a 1/10 of an inch, which contributed to a longer burn time.
Now onto our injector. So originally, in the fall 2024, spring 2025, there were some injector orifice miscalculations when we were originally starting to manufacture the parts. It was caused by a swapping of the radius for the diameter, and it occurred during, again, the original design of that injector. We were able to kind of fix that a little bit coming into the 3-second and this 10-second hot fire. We were able to manufacture some holes, some additional larger holes in the injector to hopefully raise that mass flow rate to the level that we were hoping to get it to. And there's also no O-ring between the flange and the injector, which led to gas leaks towards the end of our hot fire. And then again, the extremely low mixing of propellants was caused most likely by those holes that we had to go back and drill because of our original miscalculations. Because those holes were a little bit larger, there was a bit of a difference in the fuel oxygen ratio that we were trying to get to. So the combustion burned a little hotter. It burned pretty much next to the injector faceplate, and it caused severe streaking on the chamber and the injector itself. And also the fuel plenum O-ring melted.
All right, a little bit less of an important factor, but our hoses were too long, which caused a longer setup and made it difficult for a lot of the new crew that were working on the engine. It does add a little bit of stress to our fittings, as well as a very slight pressure loss between the ventures and the injector. And then the LOX hose is also just a little bit too short, again, inconvenient to the new crew who were unfamiliar. Easy fix within extended fitting.
I can talk a bit about the igniter failure. So during the test day, we had 2 igniter failures. These are using SDC motor igniters. They're used as a charge on the front side of the engine, right at the diverging end, right where that arrow is pointing there. It's supposed to fire that C motor into the combustion chamber and light the propellants as they come out. During injector chill, which is where we pump liquid oxygen through the faceplate of the injector to ensure that the system is chilled down to the right temperature, the high pressure and cold gas made the plastic that held the igniter on a lot more brittle than it was initially. And that led to, after excessive chilling, a break in the igniter assembly. That launched the igniter assembly off for the first fire, and we had to recycle, send new personnel out there, lost us some pressure, lost us some propellant. It could have been the end of a test day if we hadn't been better prepared. So luckily for us, we got to go again and we had a successful test, but we learned a lot from this. Numerously chilling that much is not great. Our chill temperature target was way too low. We're aiming lower than we should have. That was a fault on the test controller. Our chill targets are set so that we know we have liquid oxygen coming out of the injector to avoid a hard start. In this instance, our target was just below what it needed to be, and it caused a lot more chilling than needed to happen. Moving forward, we can raise our chill targets. Generally, they can be a lot warmer than they were. And an ASI, an integrated spark igniter, rather than an off to the side plastic igniter holder, would definitely fix this issue.
All right, to conclude our hardware review, the phenolic insert, which was probably the biggest watch item on the list, was a great success. We had no major anomalies or issues, despite some major deformation in the phenolic insert. That was attributed to other factors, and the phenolic insert itself went very well. For our silica wrapping, we would like to customize our process to our engine instead of using an older process for another engine like we did, and probably increase the thickness of the chamber to prevent that excess ablation around the diverging end especially, and hopefully that will help us maintain better thrust. Our injector faceplate needs to be improved. We're going to drastically change the orifice layout so that all of the holes are equal sized and increase the number of holes to hopefully improve atomization. Additionally, we would like to add an O-ring to the faceplate in order to improve the seal between the chamber and the injector plate so that we can prevent additional chamber pressure loss through that gap. We also would like to change the O-ring out in the fuel plenum as it melted during our test. Additionally, we would also like to get new hoses that fit a little better.
All right, that concludes the hardware review. Moving into the data review.
Yeah, so we've got a couple of very cool, awesome, lower than average unexpected numbers. As you can see here, we lost about 180 pounds of thrust, with our maximum being 641. Chamber pressure was about 100 lower than we expected it, which is consistent with the injector and fuel pressure, therefore LOX and fuel, pressure. We're both about 100, 150 less than we expected. Just a lot of things around the board. And if we go to the next slide, this first graph compares the two injector pressures belongs to the fuel with the chamber pressure over time. All three of these values, again, were dramatically lower than expected and led to a significant drop in thrust. It's likely that we had bad burn characteristics that led to low back pressure, pressurizing back up the system, allowing too much of our consumables to enter the chamber at once, lowering overall pressure, I think. So yeah, our injector pressure was, so as I mentioned before, much lower than average. We had our injector pressure drop over the actual injector itself was lower than expected, which is good. But we had a 25% drop in chamber pressure over time. If you go back to the previous graph real quick, you can see it just steadily down linear.
All right, so here we have the thrust of our graph for the 10-second duration. You'll notice that this is very abnormal. Our thrust stays very consistently close to 600 pounds of force and does not change at a linear rate nearly as much as the chamber pressure does, which would be normally expected. I think we lost about an average around 20 PS, or over time lost about 20 pounds of thrust for the duration, which is really weird. We are currently working to figure out what caused this. So we're looking through the data and brainstorming some ideas. So we're currently exploring the reasoning behind this. Some possibilities would be the drop in chamber pressure being related to a possible increase in flow separation in the diverging end. Another possibility would be the change in the throat diameter versus the change in the final diameter of the nozzle. So this lack of thrust, though it was consistent, was very proportional to the lack of chamber pressure that we started with. We'll see that there was a roughly around 25% drop in our total thrust that we were expecting. So going from 750 to roughly 600. So yeah.
All right, up here we have our pressure change for our fuel feed system. The upper line is our pressure in our fuel tank, and the lower line is the pressure upstream of the fuel venturi, and the dotted line is our average venturi pressure change across the hot fire. You'll notice that while the tank pressure mirrors the venturi upstream pressure, it is shifted about 11 psi up, meaning that we had an 11 psi drop across the feed system between our tank and the venturi. Similar for the LOX feed system, the upper line is again the tank and the lower line is again the pressure right before the venturi. And you'll notice that the gap between the two lines is much lower, meaning that we had a lower pressure drop from our LOX tank to our venturi compared to our fuel tank to its venturi. That drop was about 4 psi. So as I said, there's an uneven pressure drop between tanks to venturis, which is something that we did not really want to happen. However, upstream venturi saw very nominal pressure, which was great. That's a fantastic win for us. And we lost about 70 psi between the venturi and the injector afterwards.
Right.
Cool. So yeah, just to conclude, we lost a lot of thrust. We had a very consistent thrust over time, but we were on a much lower value than we expected. This is due to a very low chamber pressure. We also lost a lot of pressure just overall over the whole system. This can be due to a variety of factors, a couple being bad mixing. Again, the atomization was poor. There was a very small amount stolen by the venturis, but that's normal. We also had a higher and more severe and uneven ablation due to that bad mixing. If you remember the picture earlier with the streaks, that shouldn't happen. And then finally, that was our fourth attempt to do it. And so we lost some pressure in the tanks, and we had there might have been some other issues with that. But yeah, and finally, the tank pressure started at the normal levels. We want to make sure that we verify the calculations to ensure that the upstream pressures are optimal, and then that we can change those if need be.
So with changes going forward, definitely a big injector faceplate overhaul. We're definitely going to want to change those holes to get better atomization, better flow characteristics, and possibly or hopefully better back pressure into the feed system. We're going to change it from 8 holes to 12 equally sized holes with 6 pairs of holes between the injector and the LOX and the fuel propellants. We're also going to change the O-rings a bit. The fuel plenum O-ring, we're going to change the material to silicone so it can withstand more heat. We're also going to change the injector faceplate to incorporate an O-ring to seal with the flange, allowing for better chamber sealing as we're firing. We're going to personalize the wrapping procedures for our engine and wrap a little bit more to create a bit more structural stability or structural strength for the chamber. We're going to integrate an ASI system into our engine. There's currently one in development, and so we are hoping to incorporate that by the end of the semester or early next semester. We're going to update our hose hardware so that's easier to install while I stress on the fittings and hopefully create for a more smooth testing day. And finally, we're going to try to optimize flow rates and pressure calculations, run back through, organize all of the data that we have, and kind of collect everything into one organized sheet of things that we can reference going forward. And so, yeah, that concludes our presentation. If there are any questions, feel free to ask. And so, yeah, thank you.
On the slide of the graphs showing like the over time, the seconds were like the 200s since started.
Sorry?
On the bottom, the x-axis was starting at 200s. What was?
Oh, that's time. So the total.
Yeah.
So that our total hot fire was obviously 10 seconds. But the Pixie began recording at 200 seconds before.
Okay.
We start data recording when we're about to go for a hot fire. So as soon as we start really pressurizing the tanks, and usually then there's another, 200 seconds, so 3 or 4 minutes of getting the injector up to the right temperature, make sure tanks are stabilized, that kind of stuff.
Okay.
Yeah, it's because that's when the system is most dynamic, and we want to be recording data that whole time because there's plenty of stuff that can happen before the hot fire that we still want to get data on.
Cool. And then in terms of the chamber pressure loss kind of over time, is it possible that's due to the ablative loss as well?
Yes.
Okay.
Absolutely. Sorry, I didn't mention that 6%. Yes, that's one of the reasons why it's possible. That it's a lesser reason, but definitely one of them.
Okay.
With an ablative chamber, you're gonna see a chamber pressure loss the entire duration of your hot fire
Right.
because you're losing throw area.
Right.
We just saw one.
The volume increases, the pressure decrease.
Absolutely, yep.
We just saw one more than we wanted.
Yeah. It's also likely that during the burn, there was hot gas leaking through that flange interface the whole time. We could only really see it at the end when it became visible. Through the graphs, we can't correlate an exact time where it started or wasn't happening and then was happening. It's likely that it started as a small leak rate and then just accelerated. And so on that linear, it looks identical to everything else happening.
Okay.
YouTube chat, you're welcome to questions too.
Alrighty. Well, I guess if there are no more questions,
When's your next chamber wrap?
Yeah.
yeah. So going forward, we're hoping to have another chamber wrap within the next 2 to 3 weeks. It's going to be dependent on fundraising at the moment. We're currently working on some communications with the mayor of Prescott to possibly get some networking. We're waiting on a response from him. Possibly another Canes fundraiser will be in the future because that was successful and Canes responded back and said that we'd be able to do as many as we'd like to, as long as we just communicate with them properly. So yeah, that'll be our biggest thing we'll be working on and going into the future, as well as working on keeping up with the ASI, making sure that we are in tune with everything going on that side. So yeah, look out for one within the next probably 3 to 4 weeks is a better estimate.
I know, but
It will be pushing close towards the end of the semester, but we're going to try to make it work.
Yeah.
Yeah.
You ever want to fly it?
It's not gonna be our problem. That's not our problem.
Can you design a light enough rocket?
Why this is my problem?
No, I'm just asking, can you design a light enough
I'm
rocket?
sure you can.
I'm gonna be a super senior. I'm gonna pull a Charles. We're gonna start flight.
Yeah.
I'll learn something along the way.
I did a rough simulation with the Tyche engine. I was experimenting with loading liquid rocket engine into open rocket.
Yeah.
If you got a rocket that was light enough and you had like the right tank sizes, you could get it north of 10,000 feet.
Oh, easily. I bet 10,000's.
Wasn't that the original estimate for fly ropes?
Yeah.
It won't be about 300 pound thrust.
That's the one.
Yeah, so there's a possibility that Tyche could be used for a rocket in the future. However, that would have to probably be a different project or generally just a new kind of direction and overall. I think the main goal for the engine right now is just to create a reliable engine that can be used in just as a jack of all trades and just kind of be used for experimenting, and then possibly be used as the kind of poster boy for any last minute decisions or just anything that the school would need for, say, open house like we did for Spooky Hot Fire.
Yep.
Sure.
Yeah.
Yeah.
And I think,
Next question.
For future hot fires, how does someone shadow for something like this?
ask.
Message.
Like that. Just
Yeah.
like that.
Yeah, hey yo, can I be a shout out? And we're like, yeah, I don't think those slots are taken. And we're like, great.
It's
Put them on the list right now.
It's definitely going to be kind of maybe not necessarily first come first serve, but there definitely is just you gotta have that direct communication with us and say that you want to be a shadow and you're
Can I
interested.
shadow for the next hot fire?
Sure, yeah. Well, I can't promise the next hot fire. We have to get some of the members on Tyche Red Team Shadows still, but we'll try to keep one space available for people who aren't on the team for sure.
Yeah, general rule of thumb is ask the project owners, and then their team gets first dibs. Whoever, if you have open slots. We're trying to get more than just 2 people out there on a hot fire day. We're currently working with EHS. He wants to limit it to 2. If we limit it to 2, we're going to need like 15 hot fires in a semester to get everybody their shadows. And I would love that, but
Expensive.
I would like to find time to study as well.
Study that. So
So we're working on it. You also can shadow non-hot fire days as well. So like we're resequencing an engine, like we sequence Tyche at the beginning of the semester, or there's new engines coming on the test stand, or you're developing something else. Those days also, I'd like you to have at least 1 hot fire shadow, but you need 2 total. So something like that. It's a super great place to get that experience.
Yeah.
Tyche's got to resequence again.
Yep.
We got a new injector.
New injector and new ASI, so there might be multiple.
Yeah,
We'll hold off on a little bit, making any promises about that for now.
ASI test days may be limited to like 1 red deep shadow, as that is a brand new system that I would like to be as safe as possible.
Fair enough. Yeah, that's totally fair.
Along with it.
Don't look at me like that. It's also, hopefully, it's a marvelously simple system. So you don't have enough time to get the full testing experience.
Wait.
Get better. Get better.
It's going to. It's going. It's going. It's going. It's not better.
If any questions, ask Lucas.
No.
just pass around. Don't back to his
Have an autograph. Yeah. On your. Never mind.
Yeah,
On recording. We're on recording.
cool. Yeah, that concluded. Everyone, any
Really?
other questions?
Thank you, guys.
Yeah. Thanks for being here. We appreciate you guys and have a good rest of your night.